Welcome to the wonderful world of trigonometry. And today we'll talk about radians. We all know how to express angle sizes. This is a 30-degree angle, a 60-degree angle, and this one is 90 degrees. However, degrees don't agree very well with mathematics. Degrees are units, like grams, meters, or euros. They are very useful in the many application areas of mathematics, like science, engineering, economics, or when figuring out the sloping angle of your new house's roof. When left to itself, mathematics doesn't actually use any units, merely dimensional numbers. Only when we want to draw mathematics do we need a unit of some sorts, a so-called gauge, like this one. It's a two-dimensional space, so it's a double gauge, one on the x-axis and one on the y-axis. Once a gauge in place, we can use mathematics to calculate all possible lengths and surfaces in this drawing space, like the length of this radius, or the circumference of that circle. So surely, there must be a way to express angle sizes without the need for any external degree unit, or better still, without the need for a gauge. Let's see if we can find such a way. That circle radius might be a good place to start. Let's duplicate it and project it along the circle. We'll call that arc the radian. Sure enough, we can use the radian to measure angles. Let's try an angle of 45 degrees. And this is the arc drawn by a 45-degree angle. If you divide the length of that 45-degree arc, the colored arc, by the length of the radian, the white arc, you get the size of the angle in radians. It's that simple. So a 45-degree angle makes for an angle of about 0.8 radians. Let's see what an angle of 1 radian looks like. A 1 radian angle clocks in at about 57 degrees. Moving on to a 90-degree angle. The arc length of a 90-degree angle divided by the length of the radian is about 1.6. Finally, onto an extreme, an angle of 180 degrees. It measures about 3.14 radians. Now is a good time to reflect on our little formula. Let's generalize it by replacing the radian value with the Greek letter theta. Then we move the radian over to the other side. The radian is basically a curved version of the radius, so they have identical lengths. This means we can replace the radian with the radius. This formula allows us to calculate the angle arc length by merely multiplying the number of radians, represented by theta, with the radius of that arc. In this case, because it's a 180-degree angle, there's an alternative quick way to calculate the arc length, by simply taking half of the circle's circumference. That half is of course equal to pi times the radius. We can delete the radius at both sides of the equation and switch sides for readability. So it turns out a 180-degree angle is pi radians wide. That explains the 3.141 ... we measured earlier. We can apply this calculation to the other angles. A 90-degree angle is pi over 2 radians wide. And how about that 45-degree angle? A 45-degree angle measures pi over 4 radians. As a reminder, the arc length equals theta times the radius. In this case, pi over 4 times the radius. Let's use that 45-degree angle to revisit that gauge at the beginning of the lesson. Remember how we hoped we wouldn't be needing it? Well, we got what we hoped for. How big or how small that gauge is, in other words, how small or how big that circle is, has no influence on the theta of the angle. What it does influence is the length of that colored arc, the arc the angle cuts out on the circle. That arc length now equals pi over 4 times 2. But if we change the circle's size, for instance by reducing the radius to 0.5, the arc length changes accordingly, in this case to pi over 4 times 0.5. Now, if we were to pin the gauge in such a way that the arc length of that angle matched exactly its radian size, where would we put it? Indeed, right on the circle. If you now measure that arc, you'll find that it matches exactly the number of radians in that angle. This is extraordinary. It's something you'd never be able to do with those old degrees. For this reason, in trigonometry, when using a circle to illustrate angles, that circle often coincides with the gauge. Such a circle is called a unit circle. So, for reasons of easiness and accuracy, radians are expressed as a multiplication of pi with a real number. Here's a rundown of some classical angles, with their sizes measured in radians. Of course, you can express any other angle in radians. It usually makes for a slightly more complex fraction in the multiplication. For instance, if you want to convert a 107-degree angle to radians, you need to multiply the number of radians in a 360-degree angle, which is 2 times pi, with the ratio of the 107 degrees to the 360 degrees of the full circle. That about wraps it up for today. I hope radians no longer hold any secrets for you. See you next time.